Welcome to The Explainer. Today, we're diving into the invisible chemical rules that secretly run our very visible physical world. We're talking about the fundamental principles of mixtures and separations. Now, I know that might sound a bit like textbook chemistry, but stick with me. As you'll see, it's actually the hidden code behind literally everything we touch, taste, and use every single day.
Just think about this everyday paradox for a second. You start out with tall, green sugarcane plants out in a field, right? But somehow, you end up with perfectly uniform, pure, white, sweet crystals sitting in your kitchen. I mean, how does that actually happen? Well, it all comes down to the hidden mechanics of extraction and separation. It's literally chemistry happening right there on your dining table.
So here's our roadmap for today's explainer. First, we'll map out the world of mixtures. Second, we're going to look at calculating the right mix. Third, we'll dive into the rules of solubility. And finally, we'll explore the art of separation.
All right, Section 1, the world of mixtures. Before we can separate anything, we really have to understand the baseline of our physical world. The reality is, pretty much everything around us is a mixture of different substances just interacting with each other. And nature basically sorts these mixtures into two main buckets. On one side, we've got homogeneous mixtures. Think of sugar perfectly dissolved in water. The solute and solvent blend so flawlessly that the whole thing has a completely uniform composition. It is exactly equally sweet in that very first sip as it is in the last. But on the other side, we have heterogeneous mixtures. These are non-uniform. The particles just don't blend perfectly, and if you give them enough time, they will actually settle out. If you look at this in a laboratory setting, the contrast is super stark. On the left, we've got a completely clear beaker. That is our homogeneous solution, maybe sugar or salt water. It looks exactly like pure water because the mixture is perfectly uniform. But then, look at the beaker on the right. That's a heterogeneous mixture, like sand mixed into water. It's murky, the particles are distinctly visible, and you can actually already see them starting to settle right at the bottom. Now, what's really fascinating is how we can reveal the hidden nature of a mixture using something as simple as a laser pointer. If you shine a laser through clear salt water, you won't even see the beam in the liquid. But if you shine it through a mixture of just a few drops of milk and water, boom, suddenly the beam becomes intensely visible. The suspended milk particles actually scatter the light beam. It's a really simple but honestly brilliant test that makes the invisible microworld totally visible to the naked eye.
Moving right along to Section 2, calculating the right mix.
Okay, so we've talked about what is actually in a mixture, but now we've got to shift gears to the math behind the chemistry. We need to talk about concentration and specifically why getting the exact ratio is absolutely critical. And listen, concentration isn't just some dry concept for a chem exam, it can literally be a matter of life and death. For example, if a farmer uses the wrong concentration of a pesticide, mixing the wrong ratio of chemical to water, they can completely destroy their crops in the soil. But if you get the ratio exactly right, you can create miracles. Take the Indian pediatrician Dr. Dilip Malanabis. He pioneered the oral rehydration solution, or ORS. By finding the absolute perfect specific concentration of salt and sugar in a fixed amount of water, he created a solution that has literally saved millions of lives from dehydration all over the globe. So yeah, the stakes of concentration are incredibly high.
Because it's so important, industries need standard ways to talk about this concentration, and this boils down to 3 standard formulas. Now, don't worry, we aren't going to get bogged down in complex algebra here, but basically we have mass by mass, which is the mass of the solute over the total mass of the solution. Then there's mass by volume, putting the mass of the solute over the total liquid volume. And finally, volume by volume, which compares the volume of a liquid solute to the total volume of the solution.
Let's look at how these formulas are actually used in the real world. Take mass by mass. This is exactly how we label everyday solid or powdered items. Just look at this packet of commercial milk powder. Whenever you read the nutritional info to see how many grams of fat or sugar or protein are in 100 grams of the powder, you are directly reading a mass by mass percentage calculation.
But let's contrast that with liquids. On the left, we have a life-saving 5% glucose IV infusion drip. Now, because it's a solid powder, glucose, dissolved into a liquid, it relies on a mass by volume calculation. That's 5 grams of glucose per 100 milliliters of solution. On the right, though, we have a standard household bottle of 5% white vinegar. Since vinegar is made by mixing 2 liquids, acetic acid, into water, it uses a volume by volume calculation. So it's the exact same 5% label, but it relies on entirely different chemical rules.
All right, Section 3, the rules of solubility. So, we know how to measure concentration now, but what actually happens when we try to push a solvent to its absolute breaking limits? Well, that limit is called a saturated solution. It's basically defined as a solution that cannot dissolve any more solute at a given temperature. If you try to stir in just one more spoonful of salt, it's just going to sink right to the bottom. But did you catch the crucial qualifier in that definition? At a given temperature. Why is it that we must always specify the temperature when discussing how much a solvent can hold?
Well, the answer is thermal energy. Heat absolutely dictates the rules of the game here, but it treats solids and gases totally differently. As a mixture heats up, the solubility of solid solutes generally goes up, meaning hot water can hold way more dissolved sugar than cold water can. But with gaseous solutes, it's the exact opposite. As heat goes up, gas solubility actually goes down, and chemists map these exact, highly predictable changes using what we call solubility curves.
Which brings us to Section 4. The art of separation.
This is where we get to take everything we just learned about temperature and solubility and use it to pull pure elements right out of complex chemical chaos. Let's look at one of the most beautiful ways we do this in the lab, crystallization. Let's say we want to purify blue copper sulfate. Step 1, we heat water and push those solubility rules to the absolute limit, saturating it with the copper sulfate. Step 2, we filter it while it's still hot to get rid of any solid impurities. Step 3, and honestly, this is the secret sauce, we let it cool down very, very slowly, completely undisturbed. Because cold water just can't hold as much solid, the pure copper sulfate is literally forced out of the solution. And step 4, we filter and dry the resulting material. Because we cooled it so slowly, the particles had time to arrange themselves into this perfect, regular geometric pattern, leaving us with stunning, large, pure blue crystals.
But crystallization isn't just some sterile lab procedure, right? It's a massive natural and historical force. Back in ancient India, coastal communities harvested Pangara salt by boiling down concentrated sea brines, letting the water evaporate so the salt could crystallize out. And deep inside the earth, geological time mixed with immense pressure results in massive natural crystal formations. Just look at the incredible quartz deposits found deep inside the Masmai cave in India. It's the exact same chemical principle we just talked about, just scaled up by Mother Nature.
Now, what if you need to separate two liquids that are perfectly mixed together? For that, we turn to distillation. This method works beautifully as long as the liquids have a difference in their boiling points of at least 25 degrees Celsius. Basically, you gently heat the mixture until the liquid with the lower boiling point turns into a vapor. That vapor travels up and away, leaving the other liquid behind. Then you simply cool that vapor down inside a condenser until it turns right back into a perfectly pure liquid.
Let's bring this abstract science to life for a second. Take a deep breath and read this quote with me. The pleasant earthy smell that rises from the ground after the first rain. I mean, it's easily one of the most beautiful sensory experiences in the world, right? But did you know that in Kannauj, which is the perfume capital of India, they actually capture that exact scent? They literally bottled the smell of the first rain.
And how do they capture something as wild and elusive as the smell of rain hitting the earth? Well, through distillation. They use a highly traditional ancient method known as deba bika to distill the fragrance components straight out of the earth. This creates a highly sought-after natural perfume called Minti Ka Itr. It just goes to show that these complex chemical separation techniques aren't just for textbooks or white coat laboratories. They have been practiced for generations as an absolute art form.
So, we started this explainer with green sugarcane turning into white sugar, and we're ending with capturing the scent of a thunderstorm. The next time you smell the rain or dissolve a crystal of sugar into your morning tea, I want you to ask yourself, what invisible rules of chemistry, concentration, and separation will you imagine at work? Because the truth is, everything is a mixture just waiting to be understood. Thanks so much for joining me on The Explainer.